Hi guys, in this video we're going to wrap up our discussion of the simple gas laws. We talked about Boyle's law and Charles's law already, and those are P1V1 equals P2V2, or the pressure-volume relationship, and then T1V2 equals T2V1, which is the temperature-volume relationship, Charles's law. Now you'll see here, the next one, logically, we look at is the pressure-temperature relationship, and it resembles Charles's law in that it is about a directly proportional relationship. That means the ratio between these two variables is constant rather than the product of the two variables being constant. So we'll write it as T1P2 equals T2P1. That means it is directly proportional as long as volume and mole amount are held constant. So at the same volume, a higher temperature means a higher pressure. You may know that if you squeeze the trigger of one of those aerosol cans, you find the temperature drops. That's because the pressure is dropping. It gets colder as you empty the gas out of the aerosol can, and the pressure drops. That's related to this law. It's known as Gay-Lussac's law after a French scientist. It's also known as Amonton's law, another scientist in a similar era. Gay-Lussac and Amonton and Biot and Charles and several other scientists made a lot of advances in France around this time in chemistry. Let's look at a practice problem. You can see here is Monsieur Gay-Lussac avec Monsieur Biot. Whatever that number of meters in French is, de hauteur, which is depicting them in a balloon with a canary. So the picture of the canary there is so that they will know once they no longer have breathable oxygen. This is the canary in a coal mine example where coal miners would bring a canary with them, and if the canary was dead, that meant there was time to leave because there wasn't enough oxygen in the air. And we've got some other scientific equipment it looks like they've brought up with them, as well as an anchor, like the kind that would be used in a ship, which is just a really interesting sight to look at that print. So how would we go about this particular problem? Let's see if we can make a shopping list and take this equation for a test drive. It says a gas is collected at 40 degrees Celsius at a pressure of 1.19 atmospheres. So the initial temperature is 40 degrees Celsius and the initial pressure is 1.19 atmospheres. And the question then goes on to ask, find the new pressure if the temperature drops to 22 degrees Celsius. So the new pressure is what we're solving for, and the new temperature is going to be a lower one, 22 degrees Celsius. Now, first, we know that these Celsius temperatures will not work in any of the gas laws calculations. So let's go ahead and convert those to Kelvin. Now, we're going to solve for P2. The formula that I just introduced is T1P2 equals T2P1. We're going to rearrange that equation to solve for the final pressure, P2. So that becomes T2P1 over T1. We plug the numbers in, and you can see a lot of these calculations are very straightforward and very similar. Let's see what we get. So I get 1.121 or something like that. I don't know if you can see that clearly, but I'm going to round that to 3 significant figures, and I have 1.21, and the units are atmospheres since kelvins cancel. So first of all, notice that the units of pressure that I end up with are the same units that I used, and of course we could report our answer in other units of pressure if we wanted to. Both the units in temperature are in kelvins, and those units cancel. Why 3 significant figures? If you read the question the way it was shown originally, the temperature was given as 40.0 degrees Celsius and 22.0 degrees Celsius. Remember, when we convert to Kelvin, we're just going to add 273. And since that number is given to the nearest whole number, the rules for addition and subtraction state that we now know our temperature in kelvins to the nearest whole number kelvins. Since that is 3 significant figures, and I'm multiplying these numbers with another one with 3 sig figs, I can keep 3 significant figures in my answer. So you may have noticed when I wrote that number down on my paper a moment ago, I dropped a digit. The correct answer is 1.12 atmospheres, not 1.21. So I apologize for that. But again, that's 3 significant figures in all. I want to introduce a different formula, which is similar in that it looks at a relationship between 2 variables. The last one we're going to look at of this nature, and it's called Avogadros Law. It's a relationship between number of moles and volume. And it should make sense that this too is directly proportional. In other words, the more moles there are, the more space they take up. It resembles the last 2 laws we looked at. It's the ratio of moles and liters, which is a constant. They're directly proportional as long as pressure and temperature stay the same. Here's a sample problem involving Avogadros law. See if you can pause the video here and set up a shopping list and try this calculation. So in this question, we're told that 2.45 moles of argon gas occupies 89 liters of volume. And it asks, what volume will a smaller number of moles occupy? That smaller number of moles being 2.1. Well, you can see that since the number of moles is reduced by only a small percentage from the total, the volume will probably be reduced by only a small percentage as well. It's always helpful to make a quick ballpark prediction for these problems before we check it with a calculation. The formula N1V2 equals N2V1 can be rearranged to solve for final volume, and that would be N2V1 divided by N1. Let's plug the numbers in and see what we get. We get a final volume of 76.285 or so. That makes sense. It's reduced from 89 liters to a slightly smaller volume. I'm going to round that to 3 significant figures as well. We get 76.3 liters. Now, a lot of these problems are starting to look very similar. Make a list of variables, write your formula, and you can always quickly double check for significant figures and unit cancellation and see if your numerical answer verifies what we should be able to determine conceptually. So before I introduce the combined gas law, which you can see on the screen now, I want to remind you that you can often make a prediction, like I was saying a moment ago, conceptually to get a ballpark idea of what's going to happen. For instance, if we double the pressure of a gas at constant temperature and number of moles, what's going to happen to the volume? Well, doubling pressure, we'll have the volume. What if we double the number of moles? What will happen to volume with all other things held constant? Twice the number of moles of gas, according to Avogadros law, will be twice the volume. What happens if we increase the temperature of a gas? What happens to its pressure? Well, that's Gay-Lussac's law. At a higher temperature, it'll exert a higher pressure. And many of those can be fairly intuitive processes. What if, on the other hand, we're changing more than one condition at a time? For instance, if we take a fixed volume of gas and we change both the temperature and the pressure, what we get is a more complicated calculation. And when we're dealing with a fixed number of moles but other conditions are changing, we can combine several gas laws to get this one. P1V1T2 equals P2V2T1, which sounds a little bit like it has something to do with R2T2. However, it's just a combination of all the other gas laws. So let's see how each of the other gas laws we talked about are embedded here. First of all, there's Boyle's law, if you just cover up the letter T on each side. That's the first one we talked about. If we put it back and then cover up the letter P, you can see that's Charles's law, the second one we talked about. If we put back the pressure units and we hold volume constant so that it is effectively eliminated from either side of the equation, we have the third one we talked about, Gay-Lussac's law. But if, for instance, volume is not constant and we need to put it back in there, then we're going to get what we call a combined gas law. Now, I'll show you a combined gas law problem example next, and it's very similar to all the others. It's simply that we have more variables to include in our list. So here's a combined gas law problem. This is a good time to pause the video and see if you can make a list of variables and solve the problem. Notice, because this is a combined gas law problem, we're going to have a much bigger data table to make. We have changes in pressure and a change in temperature, and we want to know what the change in volume is. Give it a shot and pause the video now. So does your shopping list look something like this? We're solving for V2. We know the pressure has dropped and the temperature has dropped too. A drop in pressure would do what to volume? Let's see, Boyle's law. Lower pressure, bigger volume. But a drop in temperature, let's see, a lower temperature would mean a smaller volume. So these two changes in conditions are competing for different effects. Which one's going to have a greater effect? Well, I can still use some common sense to predict this. That's a very large drop in pressure from the original pressure, but only a smaller decrease in temperature. So the drop in pressure looks like it's going to have a bigger effect than the drop in temperature. I'm going to rearrange the equation to solve for V2. V2 is going to be calculated as P1 V1 T2 divided by P2 T1. I plug those numbers in and I get something on the order of 1,800 liters. That's a huge volume. Does that make sense? Sure it does. We've had a huge drop in pressure, but only a small drop in temperature, so the volume has increased substantially. Now, I've included two significant figures here because I actually had two significant figures in that pressure to begin with. All the other numbers have three significant figures, which means I can keep only two in this multiplication and division operation. So this might be a circumstance to consider if you are launching, for instance, a high altitude balloon. Now I'm going to put a link to a video which you might enjoy watching in which we launched a high altitude balloon in an AP chemistry class a couple of years ago. And you'll see that it actually traveled all the way from Royalton, Vermont to Grafton, and we got up to about 110,000 feet of elevation. There's some pretty cool footage in there, along with a great David Bowie song. So I hope you follow the link in the calendar to that video of our high altitude balloon launch. We had to consider some of these combined gas law calculations when we did that experiment. So as you're looking at the homework and the checkpoint in this unit, know that this is sort of an exceptionally complicated calculation where we have both temperature and pressure changing, but most of the other problems you're going to look at are just cases where you have two variables, pressure and volume, Boyle's law, temperature and volume, Charles's law, temperature and pressure, Gay-Lussac's law, and moles and volume, Avogadros law. And you can look back at these videos and look at how we've done some of the calculations and email me if you have any questions. So that's all for this video. We'll see you in the next class meeting.